So welcome everyone to, again to 60 Minutes in Space. And I actually haven't done 60 Minutes for the last couple months, but I think Steve Lee was one of the guest speakers. So for those of you who were able to make it to one of the previous ones, and maybe you saw Steve, Steve is a Mars scientist, so I think all he talked about was Mars. I'm not a Mars scientist, I'm not a planetary scientist, I am an astronomer. And so when I do these presentations, I tend to talk about things outside of our solar system. And so that's what all of our stories tonight will be, about galaxies and stars. And although actually there will be one short story at the very end about telescope observing, actually. So I'm going to go ahead and jump in and get started. If you have any questions, you can save them at the end because we should have time for Q&A at the end. But if there's something super burning that you absolutely have to ask right now, feel free to shout it out. But otherwise, please save it for the end. And Ollie, if we can have the lights, let's turn these lights at the front down or off, and we'll get started. So the first story that I will be talking about is the galaxy M51, which is a spiral galaxy, and it's very notable because it's actually interacting with this other smaller galaxy. And the reason why it has such a spectacular looking spiral pattern is because of this interaction. The idea that the gravitational interaction causes waves to sort of pulse through the disk of this galaxy, and this basically results in the gas piling up into the spiral arms that we see. Now, this is an image taken from the Hubble Space Telescope, and when you look at this image, you see lots of stars. So that's what the sort of the whitish blue glow is, and you can even make out some of the brightest stars, some of the bright star clusters, like right here, that show up as sort of white dots or specks. But you also see the spiral arms that are outlined by these dark gas clouds. And so, so these are the molecular clouds that young stars are born out of. And you can notice that there are a bunch of reddish, sort of pimple-like blobs that trace out the spiral arms. And these are locations where there's intense star formation. The young stars emit copious amounts of ultraviolet radiation, and this UV radiation lights up the hydrogen gas. And so that's why these glow in red. But because this is in the optical light, the visible light that we can see with our eyes, what this means is that there's a lot of obscuration as well. So we can see starlight, and we can see emission at the edge of the galaxy or at the part of the galaxy that's facing us, but there's a lot of material that's obscuring our line of sight that blocks the light of stars. And so what you have to do in order to see that is to go into the infrared. So this is the same galaxy from the Spitzer Space Telescope, and Spitzer recently went offline, and so it's no longer in operation. But you can see that there's still sort of the same sense, but you're seeing a lot more detail. So what we're seeing in the infrared is the glow from the gas in the galaxy. And so the spiral arms really show up, but you also see all these other patterns in between the spiral arms. So we can go back, and you notice that there's a hint of those patterns. So these sort of like spokes in a bicycle wheel that emanate out from the center of the galaxy, but those spokes are really visible in the infrared. So what I'm going to show now is not Spitzer, but the just released James Webb Space Telescope view. And so this is just the inner portion, so it's not as large of a view as what we saw earlier. And what you see is this is from the near cams. This is what astronomers call the near infrared bands. And these are typically about 10 times to, let's see, 20 to 40 times longer wavelengths than the visible light that our eyes are sensitive to. And so here we do see glow from the stars, and you can even see some star clusters. And in the central part of the galaxy is also bright in lots of stars. But the gas and dust also show up, and this gas again is lit up. It's warmed by the young stars, and so that's why you have this glow that follows the spiral arms. But now let's go to the mid-infrared. And the mid-infrared goes even deeper. So even in the near-infrared, it turns out that if you have a thick enough cloud, if there's enough obscuration from gas and dust, the infrared light will be blocked. It won't transmit through. But in the mid-infrared, it goes through most of the gas and dust. And at these wavelengths, at these longer wavelengths, we are actually seeing the glow from the gas itself. And so you're really seeing, I mean, you can almost imagine this as sort of like the skeletal structure of the galaxy, where you're seeing the dense gas lighting up, and those spokes that I was talking about, they really show up really easily here, in addition to the spiral arms. And then, of course, we still get some of these star clusters. You can see a number of bright stars, massive stars, and then there are also there's a huge density of stars at the center of the galaxy. And so this really shows you, how much detail the James Webb Space Telescope can reveal to us. And in fact, I think most of the stories tonight will involve James Webb Space Telescope data in one form or another. All right, so let's jump to a completely different topic. And this is an animation that I've shown before in past 60 Minutes in Space programs. And this is a computer simulation of a portion of our universe after the Big Bang. And what we're seeing is, as the Big Bang is expanding, gravity is causing gas to pull in and collapse in on itself. And so we are seeing galaxies being formed. And so you see these streams of gas that are being pulled in towards galaxies that are in towards the center here. But there's actually multiple galaxies. You can actually see, here's a galaxy that's plunging in, and it's going to slow down and fall back in towards this main galaxy at the center. And so when we do computer simulations of the universe, what we find is you have expansion that's taking place, but you also have collapse. And that collapse forms galaxies, it forms stars in those galaxies, and here you can even get a sense that there's a spiral galaxy being formed. And so galaxies grow over time, over the history of the universe, and the way they basically work is through gravity, although there are also other interactions as well. So if you have supernova from stars blowing off, the supernova can expel gas back into the intergalactic medium, but eventually that gas can fall back in. And we also know that at the centers of galaxies are supermassive black holes that are millions to billions of times more massive than our sun. And these black holes, when they can also be very energetic sources that can expel and shoot out gas. And that's because gas gets jammed up as it tries to fall into the black hole, and it gets heated to tens of millions of degrees. And there are physical processes that can cause great jets of material to shoot out from these galaxies. And so, and we can even run this one more time just so you can see it, since you now have a better understanding of what we're seeing. So you get a sense that everything is expanding from the Big Bang, but you can now start seeing things start to contract again. And so you can see that there are already a lot of dense points. These are the proto-galaxies that will be falling in and merging to form larger and larger galaxies. So our Milky Way galaxy, our home galaxy, a big spiral galaxy, didn't always have the same size. But what happened was over time, over the last 13.5 billion years of the universe's history, we've basically cannibalized or accreted or swallowed up smaller galaxies. And right now, our Milky Way is on a collision course with the Andromeda Galaxy, and at some far point in the future, hundreds of millions of years from now, our two galaxies will finally merge as well. Let's zoom in to a different simulation. This is from a group called Illustris, and so now we're looking at a smaller scale, and we're seeing individual galaxies instead of seeing a big chunk of the universe. But again, you can get the sense that gravity is at work. It's pulling these galaxies together. They're in orbit, orbital motions around each other, and with simulations like this, they can not only show what's happening to the gas, but they can also, they model the star formation. So they model what's happening to the gas as it turns into stars, as the stars go supernova, and the supernova eject energy back into the galaxy. And then, of course, every single one of these galaxies has a supermassive black hole at the center. And when galaxies merge, those supermassive black holes eventually merge as well. And so a big question that we have is, how do supermassive black holes get to be the size that they are today? And here we see two big galaxies merging. This was, if you remember, the one down here was more of like an elliptical galaxy. It didn't really have much gas. So the gas shows up in the spiral arms, and now the elliptical and the spiral have merged into one bigger galaxy. And so this brings us to the first paper that I want to talk about. And this is this paper came out earlier this year, so this wasn't that much of a recent bit of news, but it's indicative of a whole bunch of papers that have come out in the past year where people have looked at distant parts of the universe in different directions in the sky, and what they find is that they see a lot of bright, big, massive galaxies that existed very early on in the universe. And, you know, we've seen two different simulations of how galaxies evolve over time, and it turns out that when we look at those simulations, they predict that there should be fewer big galaxies far in the past. So it's somewhat of a mystery to cosmologists and astronomers today how galaxies grew to be really big, really fast in a very short period of time. Yes, question?
Should that be then instead of then?
More big, bright galaxy early on than expected. Yes. Thank you for getting that. So this is just one paper out of many where people found that they're finding more galaxies than is expected from what we know to be, you know, based on the conditions after the Big Bang. And so this is the fields that they looked at. The green ones are actually the ones taken with the James Webb Space Telescope. The other colored ones are ones taken from the ground. And these the red labels are relatively massive galaxies that appear to have existed very soon after the Big Bang, meaning less than 1 billion years after the Big Bang. And one of the big questions about this is that, you know, I said earlier that galaxies have supermassive black holes, and when they become very active, when stuff is falling in and material gets jammed up, they can shoot out these jets, and we see them as objects that we call quasars. And so it appears that most galaxies probably went through a quasar phase, and that quasar phase, especially in the early universe, was because there was so much more gas. Those early galaxies were especially violent. They were especially active with lots of material being shot out as material was plunging down towards the black hole. And they can also be seen, you know, from a really long distance, and so that's why it's easier to see them with powerful telescopes very early on in the universe. And so part of one of the other realizations that astronomers have had is that based on their simulations, there might not have been enough time for these black holes to grow to the size that we observed them to be. So if you think about how early on these black holes must have formed, and if the first seeds that eventually grew into black holes were started out only 100 million years or a couple 100 million years after the Big Bang. They really only had a few 100 million years to grow to the size that we observed them with the James Webb Space Telescope. And so there have been a lot of ideas about what the black hole seeds are. And you might know that black holes can begin their lives when a massive star dies. And so we know that we think that very early on, the very first stars in our universe were much, much bigger than the stars today. And those first stars, when they died, they could have formed black holes anywhere between 10 to 100 times the size of our sun. And so these so-called light seeds, if you imagine that you have enough of them accumulate, they could form a supermassive black hole. Now, another idea, and this is something that's very different, is that instead of having the black holes form from stars, there is a mechanism by which giant clouds of gas can actually collapse and form black holes without going through an intermediate stage of forming stars first. And in this case, theoreticians have looked at this. They estimate that you can form black holes with masses between 10,000 and 100,000 solar masses. So you can imagine, one of these simulations, and there's a gigantic pocket of gas, and that gas collapses to form a black hole. And they call these direct collapse black holes. So the first idea with the light seeds is you start off with a galaxy with a bunch of massive first stars, and those first stars start forming black holes, and those black holes eventually find their way towards the center of the galaxy, and they merge to form the supermassive black hole. And then the other idea is you have, like I said, a big cloud of gas that doesn't collapse to form stars. And the reason why it doesn't collapse is that there's already a bunch of stars that are forming in that proto-galaxy, and those stars are providing a lot of energetic photons, radiation, that keep this cloud heated. And when you heat something to a certain temperature, it makes it harder to collapse. And basically what happens is, at a certain point, if this cloud becomes big enough, it actually becomes gravitationally unstable so that it collapses anyway. And so this direct collapse black hole is that second mechanism that I talked about. And in this case, this is the one where you form a much, much bigger black hole. And in this case, the much bigger black hole eventually finds its way to the other big mass, which is the protogalaxy. And then so you basically have a black hole entering and finding itself to the center of that galaxy. And astronomers love to create acronyms. And so the name for this is the outsize black hole galaxy, or the OBG. And so this is the topic of the next two papers. So UHC-1 is one of the black galaxies that we saw previously in this diagram. So it's this one right at the center. And so as you can see, this wasn't observed in this earlier paper, but what the teams of astronomers did was they went ahead and asked for James Webb Space Telescope time to also observe this particular galaxy cluster. So this is done by an astronomer named Akos Bogdan, who is, I believe, at Harvard. And what his team did was they observed with the James Webb. And so this galaxy is actually part of a cluster. So this galaxy is actually in the center of this picture here. And this is a cluster of galaxies. You can see that there's a very rich cluster of galaxies. And this galaxy, if we keep zooming in, it's this one, this reddish blob right at the center, or it's not quite at the center, it's off at the one corner. But this cluster of galaxies is in the foreground. I mean, it's actually much closer to us than this very distant galaxy. And so one of the reasons why we can observe this galaxy is because this cluster, the gravity of this cluster acts like a lens, and it actually magnifies the light. And so it magnifies the light, it actually blows it up, makes it look bigger, and makes it easier to observe. And so, so all these other whitish blobs that you see here that look bigger, and even some of the smaller ones are actually galaxies that are much, much closer to us. And it only turns out that this much more distant galaxy just happens to be in the same line of sight as this cluster, and as a result, it gets magnified. So the other thing that the other observation that this team made, in addition to James Webb, is they also used the Chandra X-ray telescope. And you might have noticed that there are these contour lines in this plot, and these contour lines actually correspond to the X-ray emission. And so it turns out that there's enormous amounts of extremely hot 10 million degree gas that surrounds all these galaxies in this cluster. This gas has been emitted from supernovas. It's been shocked and it's been heated by galaxies plowing through the gas. And as a result, it shows up in the X-rays. And so this is that cluster in X-rays. And if we zoom in, we can see these squares are the pixels in the Chandra Observatory's detector. So each of these corresponds to just one pixel. And the sort of blob that you see in contours, you can see sort of a few dark lines right at the center. That's the James Webb Space Telescope image. And so you can see that the James Webb has much, much better detail or resolution than the Chandra Space Telescope. And we can even overlay the two. So here in the background is James Webb, and you can see, again, the big fat pixels corresponding to the Chandra X-ray telescope. And this is the same image as before, with the contours representing that blob of the galaxy. But you can see that there are 3 or 4 pixels that show elevated emission. So there appear to be an excess of X-rays. And from these literally, so one of the interesting things about X-ray telescopes is that when you look at how the X-ray detector actually detects photons, it literally counts individual photons. So in this case, they're seeing, I think on the order of 50 or 100 photons in each of these pixels. So it's, normally you don't think of being able to count individual photons, but you can actually do that in X-rays. But it also shows you how dim the source is, and the fact that they're able to pull out that signal from the noise is pretty remarkable. So what they figured out from both the observations with James Webb in the infrared as well as the X-ray observations, they actually can figure out how bright the galaxy is, but with modeling, they can also determine how active that black hole is at the center from the X-rays. And so from that, they can actually infer a mass for the black hole. And so in this somewhat complicated diagram from the paper, what we're seeing is the mass of the black hole, that central supermassive black hole, growing over time. So the numbers up here mean a bigger black hole than the smaller numbers down here are smaller black holes. And along the bottom of this plot, if we move horizontally on the plot, we're actually going forward in time. So the past is over here, the future is up here, and the present is probably way off past the edge of the diagram. And if you look up the top, it actually shows you the number of years since the start of the Big Bang. And so that particular galaxy, UHZ1, is just under 500 million years old. 400 some odd million years after the Big Bang. And based on our observations, this is the predicted mass of the supermassive black hole. And what these lines show are different models for how that black hole could have grown. And so the blue lines are the ones where you have light seeds. So the seeds that build up the black hole come from those supermassive stars. And it turns out that because of the ways these lines they look like they almost or at least the top half of one of these lines or these bands do intersect this galaxy, but it turns out that you have to have somewhat almost unphysical amounts of accretion happening for these light seeds to grow into the galaxy that we observe in UHC-1. Whereas if you assume that the galaxy the supermassive black hole in this galaxy started out as a heavy seed, in one of these cases where the gas cloud just collapses to form the black hole, it turns out that it becomes actually much, much easier for the galaxy and the black hole to grow and evolve to this current, or what we observe of it, just 400 million years after the Big Bang. Now, in addition to, so that's the heavy seeds. Now, in addition to that paper, another paper that just was, so neither of these papers have actually been officially published, but you can find them on preprint servers, and so they're being peer-reviewed right now. But another paper by Priyamvada Natarajan, who is a professor at Yale, and part of that same group. And again, they are looking at the same idea, where you're looking at either a heavy seed or a light seed, and this is what we observe the galaxy with James Webb about 400 million years after the Big Bang, and eventually that galaxy will evolve to what it might look like today. But what this other paper did was they actually did a really good job of modeling the what we expect to see from the light from the stars in the galaxy. So taking into account the stars, the star formation, the massive stars, and so here are their model results. And so the blue points, with the big fat bars represent the James Webb Space Telescope observations, and the red line represents their model with a heavy seed. And you can see that their model more or less fits pretty well, the shape of the expected shape that you get if you sort of eyeball these points. And so the points do more or less go through this model. And this gray line down here is the light seed model, which sort of gives you very similar line shapes, but it's much, much dimmer. So it's not as bright. There aren't as many stars as you would get with the heavy seed. So this is really the first piece of evidence that we have that the black holes that grew to be the supermassive black holes in our current day universe, sitting in the centers of galaxies, they started out not from stars blowing up, turning into black holes, and then combining to form a much, much bigger black hole. But this is the first bit of evidence that these supermassive black holes actually form from a direct collapse of gas clouds in the early universe. And now this is only one galaxy and one set of papers involving this galaxy. But as we make more observations and observe more and more galaxies, we can hopefully confirm whether this is a common process that occurred early on in the universe, or perhaps this is just something that happened very rarely, and we just happen to find one instance of this. So we'll have to stay tuned to know what the eventual consensus is, but it definitely is a big plus for people who advocate the idea that early in the universe, these giant clouds can actually collapse to form supermassive black holes. Okay, let's, since we've been talking about galaxy clusters, last year there was a press release from the Hubble Space Telescope about the earliest star that was that they think that they had detected, and this was done with an observation of this particular cluster. So it has a sort of awkward name of WHL0137-08, and so you can see the cluster, very rich cluster of galaxies in the foreground. And what we, again, are seeing is the gravity from this cluster is acting like a lens, and it's magnifying galaxies that are much, much further away in the background. And in this case, not only is it magnifying the galaxies, and you kind of see this ring or this curve, an arc of light, but they think that what they saw was a single star that was magnified as well. And so the star is thought to have existed about 900 million years after the Big Bang. So this is even older or earlier than the galaxy from the previous paper that we were talking about. That was over 400, between 400 and 500 million years after the Big Bang. So this is, actually no, this is older. So this is almost twice as old. Sorry, made a mistake. I'm going in the wrong direction. The way that they were able to get this magnification, I'm going to have to show this picture of a swimming pool. And the reason why is that, when you're looking at the bottom of a swimming pool, you might have noticed that there are these light patterns that are at the bottom. So if the sun is shining, you'll see these weird structures, almost web-like, from the sunlight. And what's going on is that the surface of the water in a swimming pool or in the ocean, you'll see this if you're diving and looking at coral reefs. The surface of the water is very rough, so there are waves on the surface, and each of those patches of water that's curved and moving around, they act like lenses. And so it turns out that when you have a very complicated surface that's acting like a lens, it can actually it can magnify, it can demagnify, and it can focus, and it can intensify and also de-intensify the light that's projected onto the water. And so what is happening, the reason why you see these very bright arcs and streaks is that the sunlight that's shining through the water, through this lens effect, that sunlight gets magnified into these very bright structures. And so instead of the sun just appearing as a spot, like you would see on, if you had like a mirrored surface on the ground, you break it up into these streaks or arcs. And these light patterns are known as caustics. And in these caustics, the light is amplified anywhere from 10 to 20 to dozens of times in the case of sunlight. Now, when you're talking about gravitational lenses, the same thing is happening where the gravity from the gas, from the dark matter, the matter in that cluster magnifies the background light. And based on the distribution of matter in your lens, in your cluster of galaxies, you can also calculate a caustic where the magnification is greatest. And so in this diagram, so we're seeing the Hubble Space Telescope image, and so this dotted or this dashed line that runs through the picture, this orange line, corresponds to the region of maximum magnification or amplification. So it turns out that just by chance, this particular star is sitting right on that magnification line, right on that caustic, and that's the reason why we're able to see it, to observe it, because normally the James Webb Space Telescope, with the exposures that it has, or the Hubble Space Telescope is able to easily observe more nearby galaxies, but it has no hope of seeing a galaxy much, much more distant, or even a star much more distant, unless it's been magnified. And so in this case, we think that it's been magnified anywhere from 1,000 to 40,000 times. And part of the uncertainty about how much it's been magnified is the uncertainty as to where exactly this caustic actually lies. And so the closer you get to the caustic, the more your amplification. And so because we don't quite understand exactly where that caustic is, this is currently our best guess, there's quite a bit of slop in what the magnification or the amplification is. So as a follow-up to the Hubble Space Telescope observation, which came out back in March of last year, just this past month, there was an announcement with the James Webb Space Telescope observation. So again, we're seeing this very rich cluster, lots of galaxies. We're even seeing more galaxies than Hubble, just because James Webb can see deeper and see fainter galaxies. And now we're going to zoom in to the James Webb view. And you might notice that they've given a name to the star, Earendel. And this was given by the authors of the paper that came out last year. And Earendel, and I'm not sure if I'm pronouncing it right, but it's actually an Old English word, which means either morning star or rising light. And if you're a fan of The Lord of the Rings and you've read a lot of Tolkien books, you might also notice its name appearing in The Lord of the Rings as well. But so based on the Hubble and the James Webb data, there actually hasn't been a paper that's been released with the James Webb data, but right now we think that this star probably has a mass of about 50 times the mass of our sun. So it's a massive star, but it's not one of these super massive stars. But what's of interest is that currently it's the oldest star that we know of, or the earliest star that appeared after the Big Bang. But the James Webb Space Telescope has only been in orbit for less than a couple of years, and so as James Webb takes more and more observations with more and more different proposals and looking at different patches of the sky, I am sure they will be finding many more record-breaking stars that will be much older or much earlier than this particular one. All right, I'm going to scoot a lot closer to home and talk about the TRAPPIST-1 system next. And this is a planetary system that was discovered about 6 or 7 years back. And this was a very remarkable solar system outside of our own solar system because it has 7 planets. And what's really interesting is that those 7 worlds, they orbit around a red dwarf, so a star that's less massive than our sun. It puts out less energy, less heat, less radiation. But all these worlds are roughly of the size of our planet Earth. And so here to scale, at least to size scale, is what we think the sizes of these worlds are compared to the sizes of the inner worlds in our solar system. We don't really know what they look like, so these are the artists' just guesses of what these planets look like. But what's also plotted are the orbits, and this rainbow-like pattern is showing the habitable zone of the 2 solar systems. So the habitable zone is basically the region based on the amount of sunlight that's coming out from the central star, whether liquid water can exist on the surfaces of rocky planets like the Earth or Mars or Venus, or any other rocky world. And so what that means is that, given the amount of sunlight, if you get outside of this habitable zone, and if you ignore what might be happening in the atmosphere, your water tends to freeze out. If you get inside the habitable zone, the water tends to boil away. So if you're interested in finding planets that are habitable to life and where life might actually exist, you want them to be somewhere inside the habitable zone. But of course, it's a lot more complicated than that because obviously Venus is right at the edge of the habitable zone and it's not really habitable by life as we know it. And Mars is on the other extreme where it's just inside the habitable zone, but it also turns out to be much colder and more frozen. And so for TRAPPIST-1, there's also a habitable zone that's been determined. And one of the big interests for astronomers is TRAPPIST-1e. If you're wondering where A is actually referring to the main star. So TRAPPIST-1a is actually the star, and B, C, D, E, F, G, and H is in the order that they were discovered. So E is not only in the habitable zone, but it's actually the most Earth-like, or most Earth-like in size. And so here's a closer artist's depiction of it, where the artist tries to make this look even more Earth-like with water and continents and clouds. But again, we really don't have a good idea of what this world looks like because we can only get so much information from our current telescope technology. So how do we know about the existence of these worlds? Well, these planets, like most planets that are being discovered today, were discovered using the transit method, where we are basically watching a star, and the star, as a planet passes in front of the star, we can see a dip in the starlight. So these stars are so far away that we can't make out any detail of the star nor the planets passing in front of them, but we can measure the amount of light that's coming from these stars. And if we see a drop in the light, and this drop reoccurs periodically as the planet is orbiting, then we know that there must be something passing in front of it. And so this eclipse or transit helps us find star systems with planets around them. Now, it can even allow us to get even more information, because if you think about what's going on during one of these orbits, so if you imagine that we're following a planet in its orbit, we're seeing the backside of the nighttime side of the planet when it's on the side of the orbit that's closer to us, and this side tends to be the nighttime side, so the side that's not lit up by the star. But when the planet is on the other side, we're seeing the daytime side of the planet. So what that means is that if you have very careful observations of the light coming from the star, which is something that you can do with spaceborne telescopes, what you find is that there's a slight excess of light that's coming from the planet when the planet is on this side of its orbit. And then when even when the planet is on this side of the orbit, there's still a little bit of light, just because we're seeing like a quarter phase of the planet. And as the planet goes to a sliver, we still see a slight amount of light. And then finally, we don't see any light from the planet when it's actually transiting, when it's passing in front of the star. And so this is reflected in this diagram here, where this diagram basically measures the amount of starlight. So again, we have a dip in the starlight when the planet is passing directly in front of the star, but there's a slight increase in the light that we see due to the reflected light from the planet. And so that's why it goes up here. And then as we see more and more of the planet, there's, again, a slight increase beyond what we would expect to see from the star. And then as the planet gets eclipsed, what we call the secondary eclipse by the star, there again is a slight dip, and so not as deep of a dip, because there isn't something blocking the star. And then the dip goes back up as you see more light from the planet. So obviously this is exaggerated, because the amount of light that you've seen from the planet is very, very tiny compared to the starlight. But again, if you have a very sensitive instrument in space where you don't have to worry about the atmosphere blurring your observations, you might be able to detect this. And even more importantly, if the planet has an atmosphere, you will see slightly different patterns than if the planet doesn't have an atmosphere. And that's because if it doesn't have an atmosphere, the planet on the lit side gets very, very hot, and then the nighttime side gets very, very cold. And so you'll see quite a bit of discrepancy in the type of light that's emitted between the cold nighttime side of the planet versus the hot daytime side of the planet. Now, if the planet has an atmosphere, what that atmosphere does is that tends to equilibrate or spread the heat around. And so a planet with an atmosphere doesn't have as extreme temperatures between the daytime and the nighttime side. And so, again, with very careful instrumentation, you can tease out these results. And so this is the paper that came out just this past, actually, it came out a couple months ago, but I thought since I haven't done 60 Minutes in Space for a few months, I could go ahead and do this because this is such an interesting paper. And the author is Sebastian Ziba, who works at the Max Planck Institute for Astronomy in Heidelberg, Germany. And when I went to look him up and I went to his website, I found out that he also created this software package that allows astronomers to basically reduce and analyze data coming from the Hubble Space Telescope, analyzing the the eclipsing data that we saw earlier. And so he calls his software Pac-Man, and he has this really amusing animated GIF showing, how a Pac-Man can eat the transit data points like you would find. So, this is a clever bit of humor coming from astronomers. And here is the data from their observations. So they used the James Webb Space Telescope, and you can see these very noisy data points, and these bigger dots is a smoothing average of all the points that were observed, and then you can see a sort of a numeric fit. That's the red line showing the transit that's taking place. But what you also find is that just like what we saw before, where you have where you see light coming from the planet when it's on the other side of the orbit, you can see that a lot of these data points are above what we would expect to see from the star. And so they did modeling of the system, and they were able to determine that the daytime temperature, or the day side temperature of the planet, was on the order of about 100 degrees Celsius, or plus or minus 30 degrees. And that corresponds to about 225 degrees, plus or minus 88 degrees. So the error bars are still pretty big. But what that means is that, interesting enough, these are within ranges that we find in our own solar system. So that's pretty exciting that we can actually measure, even with very large error bars, the temperature on this planet in the TRAPPIST-1 system. And then the other thing that they were able to do was to run a bunch of models for what the planet's emission might look like. And they only they had to pull all their data together to get just one data point for the planet. So that's what, this red diamond with the red crosses correspond to the error bars. And they have a bunch of different models. And you can see that the two models that sort of match are these two black lines that are just solid lines. They're not dashed, they're not colored, and they correspond. So one of them, it looks black, but I guess it's more like a very dark purple. So unfortunately, they did a really poor job of distinguishing the two dark lines. But one of them is this dark purple line that has a very thin atmosphere, so about 10% of the Earth's atmosphere, with a small amount of carbon dioxide. So I believe it's that top line up here, so the top solid line. And then the other line that they identify as ultramafic rock. So this is a line where there isn't an atmosphere at all, and you're just looking at just bare rock that's glowing due to the fact that it's been heated by the star. And so the atmospheric models tell us that this planet, the observations from this planet, is consistent with either no atmosphere or a very thin atmosphere. So that is kind of an interesting result because, again, this is a very distant planet, and the fact that we're able to get, with the instrumentation that we have, some idea of the makeup of this planet is pretty amazing. But it also tells us where the future is, that as our observations and as our technology improves, we'll be able to get much better understandings of these alien atmospheres and of these extraterrestrial planets in the future. All right, so my last topic is much closer to home, and it concerns the problem of space debris. So this is the only topic that I'll be talking about that doesn't involve this James Webb Space Telescope. And many of you have probably seen pictures like this that show the number of satellites and rocket parts and broken or dead satellites and random junk that's been left up in orbit. And this is quite a serious problem because even of just a few years ago, there were on the order of 20,000 objects that were bigger than 10 centimeters. So this is definitely something that should concern anyone who uses satellites or puts up satellites, and that pretty much includes everyone in this room, because even if you don't think you're using the services of a satellite, you probably are in some way. And here is a plot from a paper that came out just a couple years ago, and so their data isn't even as current as it can be, but it shows you the number of rocket bodies, so basically rocket that were launched and didn't fall and burn up in the atmosphere, so basically different stages of rockets, the actual payloads or satellites, and then in the green line is the actual amount of other debris, so things that aren't working satellites. They could be nuts or bolts or things that that an astronaut might have lost while they were doing a spacewalk, and then we also see jumps in the debris, and they actually correspond to, in one case, a test of a Chinese anti-satellite weapon where they destroyed another satellite, and it created thousands of pieces of additional debris. And then there was also a collision between an Iridium satellite and a Russian satellite that happened in 2009 that also created a bunch of debris. And so this blue line is a count of all of the satellites along with debris and rocket stages. And you might have also noticed that the amount of stuff that's been being launched has been pretty steady, but starting about 2019, it started to go up really quickly. And this has to do with SpaceX. And many of you are familiar with the Starlink satellites, and currently there are more than 4,000 Starlink satellites that have been launched by SpaceX. And these are satellites that are used to provide internet service, and it's actually not just Starlink or SpaceX that is a problem. It turns out that there are multiple companies from around the world that are planning to launch internet service satellites. And part of the reason is that it turns out that these satellites are extremely useful because during the current war in Ukraine, the troops in Ukraine are using the Starlink satellites. And there, of course, is a worry that you don't want to rely on satellites that's just controlled by one company. And so there are companies from around the world, from different countries, both China and India, are planning what are called constellations of new satellites. There is also a set of satellites being launched from the UK called OneWeb. Amazon is planning their own set of satellites as well. And if you add up all the satellites that have been announced that these companies want to launch in the near future, and by the near future I mean by the year 20 or 30, so within less than a decade, we could soon have on the order of hundreds of thousands of satellites in near-Earth orbit. And even right now, with the current number of satellites, and this some of these pictures go back to 2020 or 2021, they are affecting ground-based astronomy. So these are images taken by astronomers at telescopes on the ground where the images are contaminated by streaks coming from these satellites. And so here is a telescope that's used to monitor meteors, or basically just stares at the sky. And it sees lots of meteors, but it also sees lots of streaks coming from these Starlink satellites. And this is the dark energy camera, a large format camera that's used to observe very distant galaxies to study and understand dark energy. And you can see, again, lots of streaks associated with Starlink satellites. And even the Hubble Space Telescope is not immune to this. So this is from almost 3 years ago, where the Hubble was photobombed by one of these satellites. And it turns out that these satellites are bright enough that depending on how fast they're moving, how close they are, what the sun angle is, and where they are with respect to the sun, they can create this blur that is almost burned into the image, and it becomes very difficult to remove. And it can, as more of them get, more satellites go up, it can also be difficult to even identify them because there's so many of them. And so a paper just came out. It actually came out back in March, but I thought this was important enough to really to bring this up here tonight is the impact of satellite trails on the Hubble Space Telescope observations. And so what they did was they actually went back and looked through the Hubble Space Telescope archives to look for instances where satellite trails showed up. And so these are just a handful of examples where they found more, really bright trails that show up through a good fraction of the image, and then as well as some fainter ones. And what they also did was to map the probability of seeing a trail show up in your image. And this is kind of a complicated plot. So what we're seeing is years along the bottom, going all the way to 2021, so just a couple years ago. So even 15 years ago, there was still a couple % of the Hubble Space Telescope observations that were contaminated by satellite trails. So these numbers here correspond to percent where 1 is equal to 100%. So this is 1%, 2%, 3%, and so forth. And as you can see, in more recent years, the percentages have been going up. And as the satellite count increases, we should expect that the numbers for 2022 and 2023 should even be higher. Now, one of the things that they did do in this study was to use machine learning and artificial intelligence to try and map out or to identify satellite trails. And they were successful, but only to a certain extent, meaning out of, let's say, 150,000 potential trails or images, they might have identified, I don't quite remember the numbers, but in the end, you might have a couple thousand satellite trails that still need to be actually manually identified because the computer algorithms weren't quite smart enough to do it. And what they did also find out was that there's currently there's no perfect way to remove satellite trails. So there are some techniques that work on some trails, but because some of the trails are so burned in and they're so bright, they really can't be removed. And it also depends on the types of observations you're doing. So certain types of observations, you can remove the trails more easily, whereas other types, you cannot. And so this is a problem that will be ongoing from now into the distant future, because it doesn't look like these satellite constellations are going to go away. And so something that astronomers actually started doing about 3 years ago, back in 2020, was they started putting together working groups to try and understand this problem. And they're currently in talks with these companies to try and figure out how to make these satellites darker so they don't reflect as much. Although it's still very difficult to make them completely black. And then right now there are also no policy solutions because there are no necessarily any treaties or laws that tell industry what they can put up. It's sort of a Wild West up there. And so this is a problem that isn't quite going away, but currently astronomers are working hard to try and figure out how to preserve their telescopes in the face of this. So with that somewhat bit of negative news, I'm going to end, and I'll be happy to take questions on any of these stories. But before I take questions, I'll just point out that our next 60 minutes is the last Wednesday of September, like it is for any 60 Minutes in Space. It's the last Wednesday of the month. So hopefully I will see you there. And if you have to leave, I know it's close to 8 o'clock. Feel free to take off, but I will be happy to stay and answer any questions that you might have. Thanks. Okay, the first TRAPPIST slides. Okay, yeah, so that's a really good question. Yeah, this was discovered in order, and is it possible to discover them out of order? And the reason why this makes sense that they were discovered in order is that the way that planetary orbits work is that the closest planets orbit faster around the star. I mean, obviously, if you think of this as a racetrack, the inner track, the planet has a shorter distance to go around compared to the outer planet. It has a much bigger orbit, but the inner planet is also going much, much faster. And so in order to confirm a transit or a planet exists, you have to have multiple transits occurring. So basically what that means is that that inner planet is going to transit multiple times in the same amount of time that that outer planet, which is also orbiting slower, might transit only once. And so what this means is that in this case, it totally makes sense that you might get contamination from these other planets that are also transiting. So that's part of the problem that the astronomers have to face, is that they have to tease out these different signals caused by different transiting planets. But because this planet will be transiting multiple times, more than this planet, they'll be able to confirm this one before this one, and this one will be transiting more than this one. So in order, you'll be able to find in this case, the planets are basically discovered in order of their distance. But in some cases, there are some systems where a planet is so close to the sun, or it's so small that the signal is really noisy. And so even though it's closer in, it takes them longer to find that planet. So I think one of those systems might be 55 Cancri. 55 Cancri E is what they call a lava world, because it orbits so close to the star that we think any atmosphere it might have has mostly been boiled off, although there's some evidence that it might have silicate clouds. I think they're silicate clouds. So basically clouds made out of sand or glass. And the reason why it's E, even though it's the closest one, is that it is orbiting so close that its signal was hard to tease out. It's a world, I think it's smaller than the Earth. So you can imagine, being able to detect that planet, that dip caused by that planet amongst the noise of everything else makes it very difficult. So there's 55 Cancri B, C, and D that are much further out, but E happens to be much closer in.
And then is H about the same distance from their sun as Mars is from ours?
Let's see.
No,
Yeah, this has been enlarged, so you can see that this system is actually much, much smaller than Mercury. Yeah, so this is like I said, this is a much dimmer, redder star, so it's not putting out as much light, and as a result, its habitable zone, the zone in which liquid water can potentially exist, is actually much, much closer in. So you can imagine where that is. Yeah. So these orbits are happening on the order of days or shorter. They're not taking years like they would here in our solar system, or a fraction of a year. Yes, sir.
So this system of detecting planets, it only works when the planetary plane is
Yeah, it only works when it's edge on.
so we could be missing. I mean, that's only like what, 1% of all stars?
Yeah, that's totally true. I mean, you basically, this method only works if your solar system is, the plane of the solar system is edge on, where they can pass in front of each star. So what that means is that you're definitely right. You're missing many, the vast majority of the systems out there, and you might be able to find planets that do have odd tilts if, for whatever reason, even when it's tilted, it's still, the orbit is oriented in such a way that even when it's tilted, it's still passing in front of the star. But what that means is that if we want to understand sort of the statistics of how likely it is that there are Earth-sized planets, how likely it is for Earth-sized planets to be in the habitable zone, you have to have lots and lots of examples, just because we're only sampling a small fraction of this. And so that's why all these missions that are sent up to look for planets, they're staring at different patches of the sky, and they're looking for really thousands of planets at a time. And it takes a lot longer to confirm that these planets exist because it turns out that you have to do a lot of ground-based observations to confirm that it's a real signal and it's not a spurious signal, or it could be a variable star that just happens to be in the same line of sight that's contaminating your signal. So there are lots of things that astronomers do to confirm these planets exist. But currently, we know of more than 5,000 planets, and the numbers continue to grow. And it's only by observing lots and lots of systems that we can get good statistics that give us enough information to give us some solid science about what's going on. Okay, how about way in the back? Yeah, so once this material gets shot out, your question is, does it eventually come back? And what happens is we can actually see this in some of the simulations. Let's just go ahead. Let's go to this one. And so there are a lot of famous galaxies that have jets. So if you look at, let's see, M87 is one. If you Google that, there are a lot of Hubble Space Telescope as well as radio telescope observations of jets that shoot out quite a ways from the galaxy. So if you think of this as the galaxy, if that was M87, there's evidence of jets that shoot out, basically way out here. And so this gas is being expelled out into this extragalactic medium that surrounds these galaxies. When we were looking at the Chandra X-ray telescope image much later in the talk, when I was talking about that distant galaxy and galaxy cluster, we were seeing this X-ray blob, and that blob was coming from this 10 million degree gas. And why that gas is so hot is because you're injecting super hot gas from the supermassive black holes as well as gas from supernova into this extragalactic medium. So even though it looks like the simulation is full of empty space with galaxies flying through it, in the simulation there's actually 10 million degree gas that's part of the simulation. So you have to include that gas to make sure the simulation is realistic. And so that gas becomes part of the extragalactic medium, and eventually it could get, if it cools, it can be collected and fall back into the other galaxy, the galaxy that it originated from. But perhaps more likely it might fall into another galaxy that's part of that cluster. But if you think of galaxies as merging over time, it could eventually, that gas might eventually find its way back to the original galaxy, just because that original galaxy might even eventually merge with or swallow the other galaxy that swallowed that parcel of gas, if that makes sense. So it could eventually come back, but you'd have to follow it for millions of years to know for sure. Yes?
Going back to the satellites traffic jam that we're getting on our way to, just a couple of days ago there was a news item. England had put up an experimental satellite whose job would be to clean up some of the trash. And the experiment failed because that mission was hit by a piece of trash.
Yeah. Yeah, that's totally correct. And there are, it's not just that group, but there are a lot of people interested in trying to figure out how to reduce the trash that's up there. So it's an ongoing problem, and there are people working on it, and whether we can, whether the trash removal process can be scaled up at the same rate that at the rate that we're putting stuff up there, that's still to be determined. All right, if there aren't, okay, we have a question here.
What kind of instruments measure the temperature that allow that
Okay, so you're asking about what instruments measure the temperatures of the planet in the TRAPPIST-1 system? The galaxy or the planet? Yeah, okay. For the gases, if you see a lot of X-ray emission coming from gas, X-rays only come from extremely heated materials. So from the X-ray emission, you can actually, looking at different wavelengths, you can determine what the temperature of the gas is. And there is different types of mechanisms for X-ray emission. So you have to kind of tease that out and separate out the different processes. But measuring X-rays is actually, if you have an X-ray telescope in orbit, it's not too hard to measure the temperature of the gas. All right, if there are no more questions, I want to thank everyone for coming out tonight. And I'll see you next month. Thank you.